Okay, this is practice problem number 2 for homework number 2. This problem is directly related to practice number 1. In fact, we're going to need information from practice problem number 1 to do this problem. So let's start with what we know. The knowns are, it is yet again 10 a.m. on February 8th in Dayton, Ohio. In the last problem, we found the solar elevation being the angle from the ground to the sun, and the solar azimuth being the angle from south going east or west to where the sun is in the sky. This time, what we are asked to find is HP, being, this is the sun, the heat flux on a solar panel, which we have accounted for the tilt of the panel in all directions and the position of the sun, such that the heat flux HP we find is directly proportional to the power, the electrical power we will be getting out of our surface. So if the sun is down here and shining like this, we need to project the area of our solar panel to be normal to the ray coming in from the sun. So we are going in this problem to find the angle between the sun and the normal of the panel, theta p. Where theta p, if we multiply the area of the panel by the cosine of theta p, it projects the panel so that its area is normal to the direction of transfer of the beam, the direct transfer from the sun. We also will need to account for the sunlight that is scattered away from the beam and then re-reflected back onto the panel from all directions, or the diffuse component. So we have the beam that hits it directly from the sun and the diffuse that comes from all angles. Okay, so again, we're trying to find HP. And what I haven't added to the knowns but left space for was we know the direct normal irradiance, which is 41 watts per meter squared. This is the beam, the direct heat from the beam of the sun itself, coming directly from the sun that's hitting our panel. This is normal to the direction the sunlight is traveling, and that's 41 watts per meter squared. We also know the diffuse horizontal irradiance being the amount of heat that is hitting our panel from all directions except directly from the sun. And this is 170 watts per meter squared. So you see that the amount of heat coming directly from the sun, so if you were to look right at the sun, the amount of heat hitting you from the sun is not very much because the sun is low in the sky and it's early in the morning. But the diffuse component from the entire atmosphere is quite large because the sun's light is hitting all these clouds and being reflected onto our panel. This accounts for weather as well. In February, it's probably a day much like today where it's cloudy. And on cloudy days, you have very little input from the sun directly, and most is from reflections through the atmosphere. Okay, so to find this panel incident heat flux, we find first the amount of heat flux that is hitting our panel normal to the direction of sunlight from just the beam component, so just the part coming directly from the sun, and we add that to the heat flux that is coming from all other angles, the diffuse component, and we project that area according to the tilt of the panel, where the tilt of the panel, if this is our panel and this is the ground, is this, beta. And in this problem, our beta is 23 degrees. All right, so we need to find this term, and we need to plug in this and that. So first, HPB, the heat flux incident on our panel, normal to the direction of travel from just the sun's beam. And that is equal to HBN times the cosine of theta p, where again, cosine of theta p scales the area such that we project the area normal to the direction of sunlight. Now we're getting to something we can use. HBN is the same as DNI. So DNI, direct normal irradiance, equals the heat flux from the beam that is hitting a surface normal to the direction of sunlight travel. So all we have to do is calculate cosine of theta p, and we find cosine HPB, which we can plug in here, in order to find what we really want, HP. So let's calculate the cosine of theta p. We're going to do this up here. The cosine of theta p is equal to, this is just projecting the panel, accounting for variations in the tilt of the panel with the position of the sun, where this is alpha and this is beta. And then it's also accounting for the position of the panel relative to south, accounting for the fact that the sun is moving relative to south. So we've combined those two effects to find the complete projection, cosine theta p. And the final equation is something like this. This last part I will write down here so I don't run out of room. Okay, so the sine of alpha, where alpha again is the elevation of the sun relative to the ground. We then have beta, where beta is the tilt of our panel. Here's alpha and beta again, and then we have the azimuth of the sun, which is the position of the sun relative to direct south, and the azimuth of the panel, which is the position of the panel, the normal of the panel, relative to direct south. You can also do relative to direct north as long as both are relative to the same position. In this problem, our panel is oriented due south, which means our azimuthal angle is 0 degrees. All right, we know, let's see, did I state them from before? I did not. So, from practice problem number 1, I will put a link so that you can see where that problem, you can see me work that problem. We know that at this time and day and location, the solar elevation angle is 21.8 degrees. And the solar azimuth angle is minus 44.62 degrees, minus because it is to the east of south. Okay, so now that we know these values, we actually know everything, and we can plug all of these known values into our equation for the cosine of theta p, which again projects the area of our panel so that it is normal to the direction of the rays. We're finding the amount of area the rays are actually going to hit. And we get the cosine of theta p is 0.6. So of our total area, we have to scale that area by 0.6 to account for the fact our panel is tilted relative to the direction of sunlight. Now that we know cosine of theta p, that's really the tricky part. We're ready to plug it into this equation where HPB is given by this. So HP is equal to HBN times the cosine of theta p plus HD times 1 plus the cosine of beta divided by 2. Okay, well, we know HBN, like I wrote here. HBN is DNI, so this is DNI, direct normal irradiance. Likewise, HD, the heat flux that is incident from all diffuse components, but not from the sun, that is the same as DHI, the diffuse horizontal irradiance. I got both of these values directly from the TMY3 data for Dayton on February 8th at 10 a.m. Okay, So now that we know these two things, we know the cosine of theta p, and we can calculate this using a beta of 23 degrees. We find that the heat flux incident on our panel is 187.84 watts per meter squared. This value would be proportional to the amount of power we are getting out of the panel, and likewise the amount of heat our panel will absorb. All of these other values weren't exactly that because they were either not moving in the same direction as the panel area, and we had to adjust for that, or because they were coming from diffuse places. So, there you go. Thank you for watching.